Hello guys, welcome to another calculus video. Today we're going to be looking at this amazing integral, and this is going to be a pretty long video, so feel free to jump around, because what we're going to do in this video is we're going to start out by proving this using the beta function, and then we're going to move on to proving this using contour integration, and then finally we're going to look at how we can play around with this integral in order to get the solutions to other related integrals. So without any further ado, feel free to jump around in the video. I'll put a card for another proof in another video where I proved it using Ramanujan's master theorem. I'll put a card right there in the corner. So yeah, hope you enjoy the video. Let's get right into it. So the first proof we're going to do is using the beta function, so that's pretty simple. What we're going to do is substitute x to the n equals u, and that means that u to the 1 over n equals x, dx equals 1 over n, u to the 1 over n minus 1 du. And so we're going to have integral from 0 to infinity. Now x to the k is just u to the k over n. And then we're going to add plus 1 over n, so I'll just extend this right here. Plus 1 over n minus 1 all over 1 plus u. Now the beta function is a very cool function, and one of its properties is that if we have a beta of m and n, they don't necessarily have to be integers, equals the integral from 0 to infinity of y to the m minus 1 over 1 plus y to the m plus n dy. This is also equal to gamma of n over gamma of m plus n. And so that's what we're going to use right here. Now in this case, we can see that m plus n equals 1, and that m equals k plus 1 over n. So let's go ahead and plug in our formula. Oh, I forgot the du right here, and there's a 1 over n, of course. So for this integral, we're just going to plug in the formula. So this is beta of m is this, and n is just 1 minus m is k plus 1 over n. This is n, and let's just plug it right into the formula. So this whole integral equals 1 over n, gamma of m, so that's k plus 1 over n, gamma of 1 minus k plus 1 over m, and all over n plus n, that's just gamma of 1, so that's just going to disappear, because that's just a 1. And then we're going to use Euler's reflection formula, which says that gamma of n times gamma of 1 minus n, or I should say z, equals pi cosecant of pi n. And so this is all just going to equal pi over n cosecant of k plus 1 over n pi. And so that's our answer. Now we're going to jump into a much more fun proof, which is the one using contour integration. So for this same integral, we're going to use what I like to call a wedge contour. I don't actually know if that's really what it's called, but basically the reason we have to do this is, of course, this is going to be our integral, is when we look at the graph of, or when we look at the residues, I should say, if we solve z to the n plus 1 equals 0, that's going to give us our residues. We see that z to the n equals negative 1, or z to the n equals e to the I pi plus 2 pi I k, where k is any integer. And so our solutions are going to be z equals e to the I pi over n plus 2 pi I k over n. And it's going to be kind of annoying to deal with more than one residue, right? Because we're going to end up with a nasty sum, as you've seen in one of my previous videos of the integral of cosine x over x to the 2n plus 1. So the best way to do this is if we visualize where these are going to be. Here's our unit circle on the complex plane. For example, for n equals 1, there's just going to be 1 right here. But for n equals 2, they're going to go right here and right here. For n equals 3, we're going to have 1 right here again, and then 1 right here, and 1 right here. So n equals 1 is not a case of this integral that converges, so I shouldn't have mentioned that one. And if we keep going on and on, for n equals 4, we're going to have one right here, one right here, one right here, and one right here. And as you can see, there's always one here that's in the upper half plane for all of these cases, except n equals 1, which we don't need to worry about. So for example, we have here for 2, for 3, and for 4. And so if we can make an integral that can just capture one of these residues, it's going to make our whole integral much easier. So here's what I propose. Our contour integral is going to look like this. Here's our real axis. That's the integral that we're looking for. Then we're going to go out on the semicircle this way, and then we're going to come back right here. And the residue is going to be exactly in the middle. And so we'll call this is just going to be I, which is the integral we're solving for. This I'm going to call, I don't know, A. It doesn't really matter. And this I'll call our gamma integral, right? So the integral is z to the k over z to the n plus 1 dz equals 2 pi I res and equals the gamma integral plus I plus A. So the first thing we're going to deal with is we're going to really quickly show that the gamma integral goes to 0. Okay, so one thing that I want to mention is this is located exactly at e to the I pi over n, right? And so this radial line that we have coming out from the origin, this is actually at, I guess you could say, the argument of the complex numbers on this line are e to the 2 pi I over n. It's just double right there. And the reason that we're going to do that, you'll actually see in the moment, because it makes our whole integral a lot easier. Okay, so let's go ahead and show that our gamma integral goes to 0. So we're going to have gamma integral. Let's just go ahead and okay, we'll use the ML inequality. So the absolute value of the gamma integral is less than the absolute value of this, which is less than or equal to the length of the integral, which in this case is going to be, we're going from theta equals 0 to theta equals 2 pi over n, right? So that's going to be just, I believe, pi over n, yes? No, it's going to be 2 pi over n. That's the length of our integral. 2 pi over n times r, where r is just our limit. We're going r, it goes to infinity. That's just the radius of our large circle. And then the maximum value of this bit right here. Okay, and one way that we can simplify this is if we use our triangle inequality. We know that absolute value of z to the n plus 1 is less than or equal to, or I'm sorry, is greater than or equal to the absolute value of z to the n minus the absolute value of 1. So we know that this is less than or equal to 2 pi over n r times, now the absolute value of z to the k is just going to be r to the k. And then on the bottom, we're going to have r to the n minus 1, because the absolute value of z to the n is just r to the n on this outer circle. Okay, and now we have this limit. We're, of course, taking limit as r goes to infinity, right? And so what we can see here is that if we just bring this r inside here, now this is all constant, so we don't really need to worry about that, but these are going to infinity. So if k plus 1 is less than n, then this integral is going to go to 0. So that is our limiting factor. We do need that k plus 1 is less than or equal to n, and you can pretty much see that just by looking at the integral that it's going to diverge if k plus 1 is greater than or equal to n. So this is going to be something that's very important. We need that, and with that decided, then that means that this goes to 0, and that means that all of this goes to 0, and that means our gamma integral goes completely to 0. Alright, I'm going to make some space. So we know that our gamma integral goes to 0, so now let's work on A. So on A, we have this kind of funky wedge here. and it's going in this direction. So the first thing I'm going to do is I'm going to say I'm going to flip it so that it's going in the other direction. I'm going to like this, and then I'm going to take the negative. So we're going to do something a little bit sketchy here. We're going to say that we're integrating essentially from, so of course we have the negative sign, we're integrating from 0 to r times e to the 2 pi I over n. So remember, this is the kind of radial line where our argument of z equals 2 pi over n, right? So we're going to say that this is, we're technically integrating on a straight line, so this is sort of okay, but of course this isn't, we can't just plug this in the way we normally would. So here's what we're going to do. We're going to set z equals e to the 2 pi I over n x. Then when we find our differential, we just get dz equals e to the 2 pi I over n dx. And then what's going to happen is when z equals r times e to the 2 pi I over n, x is just going to be r, which is infinity. So this a integral is going to turn into negative. Now I'll just bring this to the outside. E to the 2 pi I over n, integral from 0 to infinity, which is just r, right, of z to the k. So that's going to be x to the k times e to the 2 pi I over k, right? All over z to the n plus 1. But z to the n, or z to the n is equal to x to the n times e to the 2 pi I to the n. And what's going to happen in that e to the 2 pi I is the n's are going to cancel, and we're just going to end up with e to the 2 pi I, which is 1. So this is just going to be x to the n plus 1 dx. And then if we bring this outside, we're going to end up with a equals negative e to the 2 pi I, oh, I'm sorry, I said 2 pi I over k. This should be 2 pi I over n times k, like that. So we're going to end up with 2 pi I k plus 1 over n times the integral from 0 to infinity of x to the k over x to the n plus 1, which is just I. Alright, so this means that 2 pi I times the residues equals I minus this e to the 2 pi I k plus 1 over n I, or I equals 2 pi I res over 1 minus e to the 2 pi I k plus 1 over n. Now here's the cool thing that we're going to do. I'm going to make some space here. We're going to multiply on the top and bottom here. Or actually, we're going to, I guess let's multiply, yeah, let's multiply by e to the pi I k plus 1 over n, so just 1/2 of this. And we're going to end up with I equals 2 pi I e to the pi I k plus 1 over n times res over e to the negative pi I, or no, yeah, we're going to multiply actually by negative that, so we'll do a negative right there. E to the pi I k plus 1 over n minus e to the pi I k plus 1 over n. And then when we divide on the top and bottom by 2i, and then this is just going to cancel right here, right? This on the bottom is just sine of k plus 1 over n, k plus 1 over n pi. Or I should say negative, actually. Negative. So I'll put a negative sign there, and then I'll convert this into sine. Alright, now this is pretty good. All we have to do is solve for our residues. So our residue is going to be equal to, remember the only residue we're worried about is e to the pi I over n. That's the only one that we captured. So it's going to be the limit as z goes to e to the pi I over n of z minus e to the pi I over n times z to the k over z to the n plus 1. And so I'm just going to split up this limit because this part doesn't have anything problematic in it and we can just plug it in directly. So I'm going to go ahead and do that. So that's going to end up being just e to the k pi I over n. And then for this bit, we're going to use the Hospital's rule because it's 0 on the top and bottom. So that's just going to end up with limit z goes to pi I over n of 1 over n z to the n minus 1. We'll bring the 1 over n to the outside. All right, and then we'll put z to the 1 minus n. And we can plug this in directly, so I'll remove the limit. And instead of z, we'll put e to the pi I over n. Okay, so first, this is going to end up just being 1 times this, right? And we're also going to have negative n pi I over n. Those n's cancel. All right. And so e to the negative pi I, that's the same as negative 1. And these are all multiplied together, of course. And so when we add this together, we're going to get that res equals negative 1 over n e to the k plus 1 over n pi I. When we multiply this in here, what we're going to get is that this is going to cancel with this, since they're negative. The exponent is negative, so it's going to cancel. And then this negative sign is going to cancel with this. So what we're going to end up with is I equals pi over n, and then 1 over sine of k plus 1 over n. Pi is just cosecant of k plus 1 over n pi. And that, I think, is just a wonderful result. I love this contour integral. This has to be probably my favorite contour integral of all time. But this video is not over because we still have a lot more stuff to go over. Now, here's the cool part. I'm going to make some space. So we have that the integral from 0 to infinity of x to the k over x to the n plus 1 dx equals pi over n cosecant k plus 1 over n pi. Now, here's what we're going to do. We differentiate both sides with respect to k. Now, of course, that's a partial derivative since we have a function of k and n, but that's not too difficult to do. And what we're going to end up with is the integral from 0 to infinity of x to the k ln x over x to the n plus 1 dx equals pi over n. Okay, when we're going to end up with cosecant k plus 1 over n pi cot k plus 1 over n pi, and of course a negative sign, right? And then because of chain rule, we're also going to multiply by pi over n again. So pi squared over n squared. And now what we can do is we can plug in whatever cases we like. So for example, a very famous integral, if we plug in k equals 0 and n equals 2, we're going to get integral from 0 to infinity of ln x over x squared plus 1, which we know evaluates to 0. And if we plug it in, we see that since k equals 0, we're going to end up with cot of pi over 2. That's just going to go to 0, and so this whole thing will go to 0. We can even take this a step further, and we can differentiate it again with respect to k, or we can plug in other cases right here. So for example, if we plug in k equals 0 and n equals, I don't know, 6, n equals 6, then this is going to be the integral from 0 to infinity of ln x over x to the 6th plus 1, and this is going to equal negative pi squared over 36 cosecant of pi over 6 cot of pi over 6, and this is equal to negative pi squared over 36. Cosecant pi over 6 is just 2. Cot of pi over 6 is, I believe, that's square root 3, yes. And so what we're going to end up with is pi squared over 18 times square root 3. So that's going to be 6 square root 3. And so that's this crazy integral, which I don't even know how I would have done it any other way other than doing some long contour integration. But because of the power of partial derivatives, we can evaluate that in seconds. Now, of course, we can differentiate this again with respect to k. We can get ln squared, for example. So I'm going to erase all this. Now, if we differentiate this again with respect to k, we're going to get integral from 0 to infinity of x to the k ln squared of x over x to the n plus 1 dx equals, now already from the chain rule, I'm just going to go ahead and make this pi cubed over n cubed, and the negative sign from the derivatives of cosecant and cot. Alright, that's quite the answer here. So if you plug in, if you go ahead and plug in, again, k equals 0 and n equals 2. I'm sorry, this looks terrible right here. I'll fix that. And n equals 2, then this part is going to disappear again. And this part will just be 1 because we have cosecant of pi over 2. And then we're going to have pi cubed over n cubed equals pi cubed over 8, which I believe is the correct answer. I'm not entirely certain. And that's not even the last trick that we can do with this. Already we have a way to evaluate tons and tons of really tough integrals, but there's one other thing that we can do here. If we go back to our original right here, now we're going to differentiate with respect to n. So what's going to happen here is we're going to get integral from 0 to infinity. Then because it's on the bottom, we're going to have negative x to the k. And then the derivative of x to the n is x to the n ln x. So we're just going to end up with x to the k plus n. And of course, this bottom part's just going to be squared. And then we're, of course, going to differentiate this. So the first term, we have product rule because we have this times this. So the first term is going to be negative pi over n squared. That says 2 squared, I'm sorry. We have negative pi over n squared cosecant of k plus 1 over n pi. And then now we have to differentiate this one. We're going to end up with negative pi over n cubed. Actually, we're going to end up with positive because we also have the cosecant cot. I'm just going to write it like that. Cosecant, that means cosecant of k plus 1 over n pi times cot of k plus 1 over n pi. And there's no really famous integrals. I'll just interchange these negative signs, multiply by negative 1 on both sides. So there's no really famous integrals that come from this that I can think of, because actually we still do need to have this k plus 1 is less than n. This still needs to hold true for this, because even though we can see that we'll have some convergent integrals where that's not true, like for example, if k just equals n, or k equals negative n, then this would converge. But unfortunately we aren't allowed to do that, just because that means taking the derivative at a point where a function is undefined. But overall, as you can see, this is a pretty cool formula. So let's say, for example, k equals 0, n equals 2, then we'll end up with the integral from 0 to infinity of x squared ln x over x squared plus 1 squared dx is going to be equal to pi over 4 cosecant of, what is that, pi over 2? Cosecant pi over 2 is just 1, so and then this cot of pi over 2 is 0, so that's going to disappear, and that's just going to be pi over 4. So as you can see, using this incredible formula, there's so many things that we can do once we have a generalized formula for an integral that we can use to turn into so many different integrals. So that's it for this video. I hope you guys enjoyed. For those of you who watched through the whole thing, wow, I'm honestly surprised because I don't think anyone would watch through this whole thing. But for those of you who skipped around, glad to see you here. Thank you for watching the video. Hope to see you in the next one, and I hope you enjoyed. Thanks!